People. Left and right. Two departments apart. Well, that's basically an all. You just do 1,000 good balls and 1,000 bad balls and then 30 others good or bad. Or red is only a word. I thought it was my horse. Yeah. Really? Well, people just have a perspective. Come up with they understand. Sometimes they don't surprise us. That's where we're at. I think it's trying to understand what's going on. You feel like create. But it's like if we know how people do this and do this, do that, we do it. It's like that right there. It's all these lessons. So it's super boring fun. Yeah.
Okay, good morning everyone. It's time to start. So first of all, we have released the deadline for the midterm project report. So if we can take a look at the canvas. Actually, we requested you to submit your midterm project report. Sorry, sure. Hello? Hello? Yeah. So we requested you to submit your midterm project report by the Friday of that week, following the fall break. So you should have like more than 2 weeks to prepare a report, and that should be enough. So just to make sure you have done some actual things, not only just, for example, creating a Kaggle account, dummy submissions, or just collect the data for your collaborative project. Because we want to say you have done a few meaningful things, like you have to try some very simple methods to submit your solution in Kaggle, or you have to try some simple baselines like linear regression or even decision trees to test on your exploratory project. And then based upon that, what do you get? Is the result satisfactory or far from what do you expect? What's your next plan? So basically, that's what we want to see. We want to see a big progress from the beginning, right? And if you feel confused or even a little bit unclear about the requirement for midterm project report, please refer to the course website. If you look at the course website, there's one tab called course project. It gives a very detailed guidance about how we expect for midterm project report and the final project report. That should be sufficient. Okay. And second thing I want to emphasize again about the homework 2. Actually, it's our third homework, which requested you to implement data boost and bagging random forest, and also collect the data to plot the learning curve, right? Training curve and testing curve. And please bear with me. So the algorithm should be straightforward to implement based upon your implementation of these trees. But it does take some time to collect the data points and to draw the training and the test curves. So I'm seeing some complaint on cameras saying that why it takes so long time to run them, because you have to generate 500 decision trees. That seems very, very long. That's the reason might be two aspects. First, your implementation is a little bit inefficient. I can tell you an efficient implementation will take no more than 2 hours. But if you like, okay, this is far more than this, you can use some trick, like you can use some lagging between the time. You don't need to collect for decision trees for every number of choice. You can set a lag to do that, or you can run it in parallel, because if you're running bagging, it's actually totally possible to run them in parallel. So, but anyway, the key point is that you do need to allocate some time to run your implementation to collect results. So yeah, so that's why I keep emphasizing that we should start early. Right? Maybe you just need 2 hours to implement all you need, but you might spend a few more hours to run your algorithm. Right? Not to mention, before you run them, you might have to debug them to make sure it is working. Right? So, and please leverage the office hours, and we have office hour every weekday. And also watch the cameras forum, right? So except for Saturday and Sunday, our TMs have their own things to do, but we do watch the cameras on Monday to Friday. I try to answer a question as quick as we can. Please don't waste those resources. Okay, any question regarding the midterm project report? Everyone's comfortable? Or everyone's ready? Okay, great. So let us continue with the perception, right? Our very first linear classifier learning algorithm, right? So we actually have covered the details, the algorithm details of perception in the last lecture, right? So here just to give a quick review, right? So essentially the perception algorithm is an online algorithm. Namely, they're gonna deal with training examples one by one, right? So we assume that we have a sequence of training examples, x1, y1, x2, y2, right? Where all input vectors or feature vectors are n-dimensional space, and yi is either -1, 1, y is labeled, right? So here I just want to emphasize again, we have augmented the original feature vector with constant 1. And correspondingly, our weak vector has included the bias parameter. The reason for doing this is just for convenience. So we don't need to explicitly write out the bias term when we do the classification, right? So just keep this in mind, because later we'll talk about the Misty Bound theorem. We use the same notation simplification. Don't get confused. So the very first step is that we're going to initialize the weight vector to be 0 vector, meaning that all the feature weights and also bias inside W0 are set to 0. Then we're going to go through the training example one by one. Right? So for the current training example, xi, yi, first we're going to use our current weight vector, denoted by Wt, to make a prediction. Right? So as I just mentioned, right, we use notation simplification. So our decision function or decision score is simply the inner product between the augmented weight vector and augmented feature vector. Right? And then look at the sign. Right? So get our prediction. If our prediction is correct, meaning that this y prime is the same as the ground truth yi, then we do nothing. Right? We just move to the next example. Right? So that's why it's called lazy learning. Right? We only update our model when our prediction is wrong. Namely, we made a mistake in predicting the label of the current training example. Right? If we make a mistake, we're going to follow this rule to update our weight vector. Right? So the updating rule is like that. Right? We've got Wt plus 1 by adding Wt, this production term, right? This product term, which is the ground truth label multiplying the feature vector, multiplying a constant learning rate R. Right? So this is a very simple update, a simple updating rule. And we actually can classify this into two cases, right? So if this ground truth label is positive, meaning that we have made a mistake on positive example, then y is 1, right? So essentially we add the current weight vector, this r times the input vector to get w plus 1. Right? If our ground truth label is negative, then yi is minus 1, right? So we'll subtract the current weight vector by r times xi to get a new weight vector, right? So we have explained the rationality of this update, both in an algebraic way or geometric way, right? So we actually spent quite a amount of time in the last lecture explaining why doing this update indeed helps, right? It actually helps you to overcome this mistake, right? So I'm not going to repeat this. And also we show geometrically how after some updates the weight vector changes and causes the change of the decision boundary so that we can correct the mistake, right? So I really suggest you to look at those geometric interpretation because it's very intuitive and can help you understand why this update is reasonable. So those are our perception algorithms. We know that this is really simple, straightforward, but it's also classic and effective, right? And then we talked about some convergence guarantees about perception, some theoretical guarantees about perception, right? So that leads to two theorems. One is called convergence theorem. The other is called cycling theorem. Right? So these two theorems actually describes the behavior of perception when you use that to learn classifier from data. Right? So what does convergence theorem say? So basically says if the data is linearly separable. In more detail, if there exists a set of weights that are consistent with the data is linearly separable, then the perception algorithm will always converge. Right? So no matter how you stream your training examples to your to the perception in whatever order, it always converges. But what if the data is not linearly separable? Right? So this case is actually quite common. Right? We cannot expect the data is so good. Right? It can be perfectly classified by linear classifiers all the time. Right? So if the training data is not linearly separable, then the perception learning will not stop. Does not guarantee to converge. If you keep running and does not enforce it to stop, what will happen? Finally, it will end up with infinite loop. Right? So in this cycle, it just cyclically goes through a set of distinct weak vectors. Right? So you can imagine there's weak vector here, weak vector here, weak vector here, weak vector here. Right? So just enter this loop, and the switching between those distinct weak vectors never ends. And so in practice, of course, you have to always set up the maximum number of the updates or maximum number of iterations, etc., right? to avoid your perception keep running forever. Right? After all, there's no guarantee that every data set is linearly separate. Okay. So we're more interested in the case of the convergence. So when the data is linearly separable, we know the perception will converge finally, right? But how many updates will the perception do, right? In other words, how many mistakes will perception make? Right? Remember, in the perception algorithm, it makes an update whenever it makes a mistake in predicting the current example, right? So that will lead to a more detailed theorem. It's called Misty Bound theorem. And to introduce Misty Bound theorem, we introduce the concept of margin, right? So this is a very, very important concept. Right? And we'll repeatedly use this concept to illustrate the idea of the perception, and also as the support vector machines we're going to discuss later. Right? So the margin of a hyperplane, for a data set is the distance between the hyperplane and data point nearest to it. So basically it says the margin is first a property of a separating hyperplane for a particular data set. So if this data set can be separated by the hyperplane, then we can say this hyperplane has a margin for this data set. You cannot say a hyperplane has a margin. Has a margin for which data set? You must bind it to a data set which can be linearly separable by this hyperplane. And then the margin is defined as the smallest distance between the data points in this data set and this hyperplane. So this is the definition of margin, and then we can generalize this idea, this concept to the margin of the data set. So here, the margin of the data set represents the intrinsic property of the data. So first of all, when we say a data set has a margin only when the data set is linearly separable. So if the data is not linearly separable, there is no margin. Okay? And next, if the data is linearly separable, what is margin? We just look at all possible separating hyperplanes for this data set and use the largest margin of those separating hyperplanes as the margin of the whole data set. So this is still serves as example, right? So this data set obviously is linearly separable. So say this data set has a margin. Right? What is the margin? We just look at all possible separating hyperplanes, like this black lines, like this blue lines, and each line has its own margin, right? So just to pick up the largest margin among all those separating hyperplanes, and that margin is defined as the margin of the whole data set. So the margin of the data set actually describes the easiness to classify this data set, right? So you can imagine the larger the margin of the data set, the further apart the positive examples, negative examples. Meaning that the easier you find the separating hyperplane. Right? So later we'll look at this concept of margin again, right? And especially when we talk about the generalization error bound, and it's actually closely related to the margin. Okay. And also we reviewed the definition of the distance, and remember, because we're discussing everything in augmented feature space. Our decision function is W transpose X. The bias parameter is included in this augmented weight vector, and correspondingly, the input X, input vector X has included a constant feature 1, so quadratically our distance can be computed in this way, right? So now let us look at this Misty Bound theorem. Right? So it is kind of like a long statement about that theory, but it just includes 2 preconditions. And based on these 2 preconditions, we can create or make an upper bound for the number of mistakes by running rounding perceptron. Okay, so the first precondition is that, okay, suppose we have this M training examples, okay? And each feature fit vector, its norm has upper bound, finite upper bound, which is R, okay? And label is -1 or 1. Okay? So this is actually a pretty reasonable. I mean, it's not just theoretical; it's pretty reasonable because in practice we'll never have a feature values to be infinite, right? So that means to find this upper bound R is pretty straightforward. You just look at all the inputs, right, in this n-dimensional space, and which one is the farthest from the origin, right? You just use the norm or length as R, right? And the second precondition says that suppose there exists a unit vector such that for some non-negative gamma or positive gamma, we have for every training example this inequality holds, right? So yi times u transpose xi is no less than gamma, right? So what does this second precondition mean? An idea?
That it has margin gamma?
Yes, right? So this is actually saying, okay, 2 points. First, this data set is linearly separable, right? Secondly, and there exists a hyperplane which is represented by this unit vector u, which can predict all the training examples, right? And also, we want for every training example this inequality holds. But remember, the left-hand side actually defines the distance, right? So if we look at the distance definition here, right? So if because we're doing everything in the augmented feature space, the distance between any feature vector and this hyperplane H can be written in this way, right? And here, if we replace W by U, remember U is unit vector. So actually you don't have this denominator, because you know what denominator is simply 1, right? And also because you can correctly classify all the training examples, you don't need to write down this absolute value because it is equivalent to the label times the score, right? So if you correctly predict every training example, this product is always positive, right? So the left-hand side of this inequality simply means the distance between xi and this separating hyperplane represented by u, and says that this distance for every training example should be no less than gamma. Implies that the margin of this separating hyperplane represented by u is at least gamma, right? So that's the idea. So basically, the second precondition is saying that, okay, this data set is linearly separable, and we know that there exists a separating hyperplane whose margin is gamma. And now, given these 2 preconditions, we can claim that the perception algorithm will make at most R over gamma squared mistakes. So just divide the maximum length or maximum norm of the feature vector by this knowing gamma, knowing margin, right? And then take square. Then this serves an upper bound of the number of mistakes for running perception algorithms. Any questions so far in understanding of the Misty Bound theorem? Everyone's good with that? Okay, great. So yeah, just emphasize that that's something we have all. And one thing I just want to mention again. So here we choose the weight vector for the separating hyperplane to be a unit vector simply for convenience. If you if you don't want U to be univector, then in your Misty Bound you have to include the norm of U inside this bound. Okay? So we're going to go through the proof in the details, and later you might be requested to give a modified proof by including this non-unit vector U, meaning that we're going to ask you to derive this Misty Bound when the separating hyperplane is represented by a non-unit vector U is not normalized. So the proof details will be, the proof techniques will be almost the same. Okay, so in general, I mean, in a very rough way, Misty Bound theorem tells us that suppose we have a binary classification data set with n-dimensional inputs, and if the data is separable by linear classifiers, then the perceptual algorithm will always find a separating hyperplane after making a finite number of mistakes. This is very meaningful in theory, because we can now say we do not want to expect it might converge after infinite number of updates. Right? If it converges at an infinite number of updates, it is only meaningful in theory. It's not meaningful in practice. Right? Okay, so now let us look at the proof. So because this is a very fundamental proof, and it's very important for perception, so we request everyone to understand the details of the proof, and also is able to modify the proof a little bit to adjust it to the variance of the preconditions. So here's the setting before we go to the proof. So first, we initialize the weight vector W as 0, all zeros. Remember, the weight vector is augmented with the bias parameter, so the bias parameter is also initialized as 0. And for convenience, we just set learning rate R to be 1. So the updating rule here, which is the omit R for simplicity, but the result won't be changed if you just include R. And the two preconditions for this theorem. First, all the training examples are constrained in a ball of size R. So basically says every training example, the norm of its feature vector is upper bounded by R. Right? Remember, the norm of vector is the length of vector in the Euclidean space, more rigorously. And the training data is separable by a margin gamma using a unit vector U. So basically says, okay, the training data is linear separable, and there is a hyperplane described by some unit vector U whose margin is gamma, right? So this is equivalent to saying that the distance between every training example and this separating hyperplane is less than gamma. So to show this to derive this Misty Bound, we actually need 3 steps. In the first 2 steps, we're going to show 2 inequalities. In the third step, we just combine these 2 inequalities to form a new inequality regarding the number of mistakes, and then we solve that inequality to get this upper bound. That's the idea. So what is the first inequality we want to show? So we claim that after making t mistakes, then the inner product between U and the current weight vector Wt is no less than t times gamma. U, remember, is a unit vector which represents the separating hyperplane of this training data, right? And gamma is margin. So how do we show this? We use induction. Right? We have practiced the induction trick in our homework 0, right? So now you can see why those reviewing problems are useful. To just remind you of these tricks we have learned since high school, right? So how can we conduct induction? Right, we need to do 2 things, right? First, we assume the conclusion is correct at step t, right? And then based on that induction assumption, if we can show that when we move to step t plus 1, this inequality still holds. Right? That's the first thing we do the induction for the for proving things, right? And second thing is that we just need to verify at early beginning, very first step when t is 0, the result is still correct. And then you finish the proof with induction, right? So two things. First, given the induction assumption, then you can expand your results to the next step. Okay? And second thing, just verify at the beginning this induction assumption is correct. And then you can imagine it's kind of like propagation, right? From step 0 it corrects, and then from step 0 you can show step 1 is correct, and from step 1 you can show step 2 is correct, and it goes forever and ever. Right? That's the idea of induction. So let us apply the induction technique to show this inequality. Right? First, we're going to assume, okay, this inequality is correct when you only make t mistakes. Right? And want to see that when you make t plus 1 mistakes, will we still have this inequality to be correct, right? So how can we show that? Remember when we run the perception algorithm, when we make a mistake, right? So we got wt plus 1 equals to wt plus yi xi, right? It's just simply applying the perception updating rule, right? So now, at step t plus 1, we'll evaluate the left side of this inequality. We just substitute the right-hand side of updating rule for wt plus 1, right? So, and then we get this left-hand side can be expanded as the summation of the inner product between u and wt, the previous V vector, plus yi u transpose xi. This is essentially to do u transpose over these two terms, right? So you got yi u transpose xi. So now, if we take a look at our preconditions, first we know that this term is no less than gamma. Okay? This is our second precondition. We require that the margin of the separating hyperplane represented by u is at least gamma, right? That basically says, okay, the distance between any example xi and the separating hyperplane, which is this term, right, is no less than gamma. So you immediately get a lower bound of this right-hand side, right, which is u transpose wt plus gamma. Right? And what's the next step? Any thoughts? What can we observe? I can't hear you.
Is it because if the u TWT is bigger than equal to t times of gamma, and if you put the gamma out, then you get gamma multiplied by t plus 1, and hence becomes 2?
Yes, exactly, right? So remember, we need to average the induction assumption, right? That is, we assume, okay, after t mistakes are making this is made, this is correct, right? So this is induction assumption. By applying induction assumption, we know, okay, u transpose wt is no less than t gamma, right? You t gamma plus gamma, you got a new lower bound, which is t plus 1 gamma, right? So t plus 1 gamma, obviously, is consistent with the result for step t plus 1, right? So we know that. So now we can show that if we assume after step t, u transpose wt is no less than t gamma, then when we move to t plus 1, we have u transpose wt plus 1 no less than t plus 1 gamma, right? So we finish our first stage, right? That is, the induction is correct when at step t, and then the induction is correct at step t plus 1. Then the remaining thing is just to check at the early beginning, right? At the very beginning, if this inequality is correct, right? Which refers to t is 0, right? So if t is 0, is this inequality correct? How can we verify this? When t is 0, what is left hand side? Remember, at the beginning, we initialize all the weights to be 0, right? So W0 is simply 0. So when t is 0, left hand side is simply 0, right? And how about the right hand side? It's also 0, right? So when t is 0, I mean, at the very beginning, this infinity here is still correct, right? And then we have just to show that for any step t, if this is correct, then for step t plus 1, this is correct as well, right? So now we finish the induction. Right? We have used the induction to show that this infinity holds for any number of mistakes t. Any questions so far? Is everyone comfortable? It's just a direct application of the induction. Okay, so now let us look at a second inequality we want to prove. That is, after making t mistakes, the norm, the square norm of the current weight vector will be upper bounded by t times r squared. Right? Here, r is the upper bound of the norm of the, the training input vector. Right? So how can we show that? Again, we use induction. And first, we assume that after at step t, this holds, right? We're going to look at t plus 1 if this still holds, right? So again, when we look at the square norm of wt plus 1, we know that wt plus 1, because it has made a mistake, right? So wt plus 1 is actually wt plus yi xi, right? Just substitute into this inside the square norm, and you expand it, right? So we got three terms. First, the square norm of wt, previous weight vector, and the square norm of this yi xi, right? So yi squared is simply 1, no matter if it's positive or negative. And then you got a cross term, right? Which is 2 wt transpose yi xi, if you just move y out. This is just the expansion of this square norm. And we can take a look at this two terms, right? So first, this term is negative. Why? Why this is negative? I heard that. Because you're making a mistake, right? So you only when you make a mistake, you update your weight vector to get wt plus 1, right? So you're making a mistake in predicting xi, meaning that this product is negative for sure, right? So yi wt transpose xi, y is a ground truth label, and this wt transpose xi is a decision score, right? So if you make a mistake, the product is always negative, right? So you got this one is negative, and this part, the square norm of xi. Remember, according to our first precondition for the theorem, we know that it is upper bounded by r, okay? R squared. So now the right hand side, this summation immediately gets a upper bound, right? This one is less than 0, and this one is less than r squared. So it is upper bounded by the square norm of wt plus r squared. So now what's the next step? Any thought?
We can use our hypothesis.
Yes, exactly right. Remember, always leverage our induction assumption, right? Our induction assumption, I'm assuming that okay at t step, right? T mistakes, we got this host, so wt is square norm is upper bounded by t r squared, right? Plus this r squared, we got t plus 1 r squared, right? So t plus 1 r squared, this actually shows that at step t plus 1, the inequality also holds, right? So we finished the first thing of this induction, right? Then the remaining thing is just to verify at the very beginning, that is when t is 0, this inequality here is correct. And when t is 0, okay, we know w0 is simply 0, right? So the square norm is 0, and t r squared is simply 0. So this inequality here is correct since very beginning. And then we have shown the correctness. Any questions? Okay, so now through the first two steps, right, we have derived two inequalities. Each inequality talks about the number of mistakes t, right? So the third step will be to connect these two inequalities together, right? To derive a third inequality about the number of mistakes t, right? So how can we do that? We start with the second result, right? We take the square root on both sides and also revert to the direction, right? So basically we can know that if you take the square root over the right hand side, we know r square root t is no less than the norm of wt. Just to take the square root over square norm, it's just norm of wt, right? And next we're gonna apply the so-called Cauchy squares inequality to get a lower bound of the norm of wt, which is simply u transpose wt. How can we do that? So remember, this is from just try to recall what you have learned from the high school, right? So in the n-dimensional space, right? So when we calculate the cosine of the angle between the two vectors, the general formula is here, right? So we know that inner product between the two vectors is equal to the norm of these two vectors multiplying the cosine of the angle between the two vectors. So if you want to calculate the cosine of the angle between actual two vectors, you just divide the inner product by the product of their norms. Right? So from this, we can see that because in our case, the unit vector u is unit vector, so this norm is simply 1, right? And the cosine is always less than 1, right? Less than or equal to 1. So we immediately get this inequality, that is inner product is upper bounded by the norm wt. This one is 1, this one is less than or equal to 1. So we immediately get the left hand side is less than or equal to the norm wt. So this is called Cauchy squares inequality. Now if you apply this Cauchy squares inequality here, we immediately connect these two equalities because the u transpose wt is the left hand side of the first inequality, right? So now, from the left hand side, left end and right end, we can connect the two terms together to form a new inequality. So what's the usage for that? We just solve this new inequality about the number of mistakes t, right? So we immediately get this upper bound, namely t upper bounded by r squared over gamma squared. That's how we show the Misty Bound. So any questions so far?
I'm trying to see. Oh no, never mind.
You're trying to see.
I'm trying to see why you showed all this stuff about cosine.
Oh, this one?
I see why you showed it now. Yeah.
Oh, this one is just the knowing result.
Now let's get that left side in the middle, and I was unclear about that.
This one? You mean this one?
Just in the middle of your equation up top there, you have the inequality sign. I was trying to figure out how it was relevant. The stuff you put here, now I understand it because it's less than 1.
Yeah.
So yeah,
Okay.
thanks.
Okay. Yeah. I mean, if you feel a little bit slow to catch up, that's fine. I mean, just to relook at the slides. It's just based on this result. This is a knowing formula, right? And then because in our case, remember the u vector is a unit vector, so the norm is simply 1. The cosine is always less than 1, right? So we know that this right hand side, this product is less than or equal to the norm of wt. Right? So of course, the u transpose wt is upper bounded by the norm of wt. Right? And in this way, just to connect the two inequalities, And then you just solve this new inequality about t. You get this upper bound. Yeah, this is a very important theorem, and probably is the only theorem we request you to know and understand, and yeah. So I would suggest you to look into these proof steps, which is really not hard, and understand it. Okay, so in this way we can bound the total number of mistakes in running perceptron. Remember, this whole proof has nothing to do about how you're going to stream your training examples to perceptron. You can use whatever order to feed the training example to perceptron, but it doesn't matter. The number of mistakes t is always bounded by this. Okay, now let us relook at this Misty Bound theorem, right? So basically, we have two preconditions, right, to get this bound. First, we assume that all the feature vectors, their norm or length is upper bounded by R. R is a finite number, which is easy to find. You just look at the input points, say in an n-dimensional space, which one is farthest from the origin, right? Use that norm as the upper bound. And secondly, we assume that the data set is linearly separable. So there exists some separating hyperplane that can be represented by a unit vector U whose margin is gamma. And then we can create a bound of the number of mistakes made by perceptron. Remember, the number of mistakes is actually the number of updates. Perceptron only updates the weights when it makes a mistake. So this upper bound is simply R over gamma squared. So here we want to give a more intuitive description of this bound to give you a sense, right? What does this bound mean? Right? So here are the training examples. Positive examples, negative examples. Obviously, this data is linearly separable, meaning that okay, if you run perceptron on this data, it will converge, right? It will give you a separating hyperplane. But how many updates or how many mistakes will perceptron make? Right? So to estimate bound, first we're gonna find R, right? The R is the upper bound of the norm of the input vectors. When we do that, we just look at which training input is farthest from origin, which is turned out to be this positive example, right? So we got R. So what does that mean? It just means all the training examples are actually included in this ball, right? In this sphere with radius R, right? So actually R indicates the span of the training examples. And next, if you want to estimate bound, right? So we need to find a separating hyperplane. So here, just a random find the separating hyperplane is black line, right? And notice separating hyperplane has a margin gamma, right? So margin is, remember, it's the minimum distance between the training points and this separating hyperplane. Right? This margin gamma. And then by using R and gamma, we can bound the number of mistakes R squared over gamma squared. So intuitively, you can see, because this is gamma, roughly indicates how far away the positive and negative examples inside this data set, right? It's kind of like inner separability within this data set, right? And this big R actually represents the outer span of the whole training data points, right? Then your number of mistakes is upper bounded by this R or gamma in X squared. Hopefully this will give you an intuition about this mistake bound. Any questions so far? Is everyone comfortable? Okay, great. So this bound can help us to estimate the cost or the cost of running perceptron, right? So, for example, if I want to use perceptron to learn a particular type of objective functions or target functions, right? We can estimate how many mistakes at most it will make. Right? For example, if your target function is a disjunction of n attributes, right? And suppose you have fed like all to the power of n Bloom input attributes, right? Suppose you have n attributes, and each input feature is binary, true or false, right? So, of course, in your whole input space, there will be 2 to the power of n input space, right? Input vectors, right? Suppose you feed all these 2 to the power of n input vectors to our perception, how many mistakes can we make? How can we estimate this? Just applying the Misty Bound theorem, right? We just need to find, okay, among all these 2 to the power of n input vectors, what is R, right? And secondly, we just find a separating hyperplane, right? And get one gamma, right? Then we can construct the upper bound mistakes. Just application of the Misty Bound theorem, right? So here we just want to use one example to illustrate how to do that, because our homework will request you to do such kind of problems to deepen your understanding of Misty Bound theorem. Right? So suppose this is our target function, right? x1 or x2 or xn, right? So we know that this function is linearly separable, right? When we discussed the expressiveness of linear classifiers, this function is definitely linearly separable, right? We know how to find a separating hyperplane, which we will revisit later, right? So first, to estimate the upper bound, we need to find R, right? The upper bound of the length of the input vectors, right? So what is it? It's simply square root 1 plus n, y.
The biggest one would be the one where everything is 1.
Yes, right? So remember, we discussed about this, right? We just define the point, the input point or input vector, which is farthest from the origin, right? So which input vector is farthest from origin? When all x1, x2 to xn are 1s, right? And remember, we are doing everything in the augmented feature space. So you have to augment the feature vector with 1. So you actually have n plus 1 once, right? So that's why R is square root 1 plus n. And then we need to find a separating hyperplane, right, which can separate all these positive examples, negative examples labeled by this disjunction, right? So how to find a separating hyperplane, we have actually discussed before, right? So we know that this function is 1, meaning the label of arbitrary input vector is 1 if and only if any of those variables is 1, right? So equivalently, it is to say this inequality is no less than 1. Right? So x1 plus x2 to xn is no less than 1. So we can move 1 to the left-hand side, we get our classifier, right? So we have a w1 to be 1, w2 to be 1, and bias term to be minus 1. So can we use this classifier, construct a separating hyperplane, and then construct the upper bound? The answer is unfortunately no. Why? The reason is margin 0. So why is margin 0?
Because there's an example where that's exactly true. Like if x1 is true and all
yes.
that.
Yes, exactly right. So just be careful. We can use this trick to construct a separating hyperplane. But it is possible to pass through several training examples. Remember, the margin is the minimum distance between the training examples and the hyperplane, right? If the hyperplane passes through that example, the distance is simply 0, right? If your margin is 0, then your upper bound is infinity, right? Your upper bound is infinity, well, it's not wrong, but it's meaningless, right? So if you take a look, if I choose x1 to be 1 and all the other input variables are 0, so you know that this decision function is simply 0. The basis says, okay, this vector, this input vector, stays right on the separating hyperplane. So the margin, that means the margin of this separating hyperplane, but this data set is simply 0. And then it leads to a meaningless mistake bound. Right? So how to avoid this problem? We just try to move this separating hyperplane a little bit. So I'm going to choose to move it by half. So my new hyperplane will be represented by this. So x1 plus x2 to xn subtracted by half equals to 0. Now we can guarantee no training points will stay on this hyperplane. Why? Why?
Booleans are 1 to 0s.
Yes, exactly right. You just look at the type of variables. Remember, every x1, x2 to xn is either 1 or 0, right? So their summation must be integers, right? No matter you choose how many 1s you choose, how many 0 you choose, right? Their summation must be an integer. An integer subtracted by a fraction will never be 0, right? So that guarantees that, okay, there's no points will be stay rightly on this hyperplane, right? Because this includes one host for any choice of the input examples. So then we can calculate margin. What's the margin? So first, we need to normalize the weight vector here. Okay. So here, if we do not normalize weight vector, well, we cannot directly use the Misty Bound, right? So to normalize weight vector, we just calculate norm of weight, right? Remember, we augment our weight vector with this bias parameter half, so this minus half is appended to all these lines, right? And now we just calculate norm this weight vector, right? So it's n plus 1/4, right? We have n attributes plus force, right? If you just divide this vector by its norm, you got unit vector u, right? And you got our unit vector u, right? And then you just find which is the closest point to this boundary. So which point is the closest? We don't need to take a look at this fraction, just take a look at here, right? Because no matter you skew the weight vector by any positive number, it won't change the direction, it won't change position of the hyperplane, right? So now you can tell me which choice of x1 to xn will make this point closest to the hyperplane.
They're all 0, you can't get closer than that.
Yes. Any other thought?
A single one also.
Yes. Right? So either all x1 to xn are 0, right? Or a single attribute is 0. It is 1 and all the other zeros. In both cases, their distance is the same. Why? Because if you put all x1 to xn to 0, right? The left hand side is just half, right? You need to take absolute value. Right? Or if you take a single attribute to be 1, all the remaining to be 0, it's half, right? But if you take more than 1, right? Like 2 or 3, remember the right hand side is increasing, right? Mount target is increasing, right? The left hand side value will be bigger and bigger. So remember, we choose the smallest distance. So you need to choose the setting of x1 to xn minimum value to be as small as possible, which can hold up two cases. First, you make all x1 to xn to be 0, or you only have one attribute to be 0, to be 1. Okay? So you got half over this square root n plus 1/4 is your gamma. And finally, you just use R, where is R? R here, and gamma here to construct the upper bound of mistakes. Okay, any question regarding how to apply the Misty Bound theorem? But in summary, it's just 2 steps. First, you're going to find an upper bound of the length of the input vectors. Secondly, you just find a separating hyperplane. Just be careful. Don't choose a hyperplane where some points just directly stay on the hyperplane. That will lead to 0 margin. You need to move the margin a little bit to ensure that no points is on the margin, so you have a non-zero margin. So then you can construct a meaningful upper bound of the number of mistakes. Okay. Okay. About this theorem, what you need to know is that, okay, what is perception of Misty Bound and the proof details. So the last topic about perception is some practical variance. So when we apply perception in practice, how do we implement them? Or how do we modify them to be more robust, more accurate, right? After all, because our course is more toward the practice, right? We need to know practically how you apply it. So we're going to talk about 3 versions. First, when you implement or when you use perception algorithm on a finite data set, how we're going to implement it. And secondly, we're going to introduce 2 variants of perception, which is really better than the original perception. One is called margin perception, and the other is called voting and averaging perception. Okay. So first, if you want to apply standard perception practice, how are you going to implement them? Okay? So you need to explicitly specify a number of epochs. So what is epoch? One epoch means that you need to pass through the data once. Right? So remember when we talk about the original or ideal version of the perception, we just assume, okay, you're going to stream the training examples, right, to the algorithm. But in practice, your data set is always finite, right? You stream them once, you finish pass once, right? And then you need to stream them again, right? So that means you go to the next iteration or epochs until the maximum number of epochs is achieved, right? So you need to set up this. You need to set up the maximum number of epochs, right? Because you cannot guarantee it will just do not make any mistakes and stuff, right? So, and then during each epoch, a good practice is to random shuffle the data, and then feed this training example with a new order to the perception and do the update. Right? The reason is just to balance the different kinds of orders. Do not make your update biased toward one particular order, so that it can be more robust. And here, we use this inequality to simply indicate the mistake. Right? Remember, we have discussed this previously. If you make a mistake, then the ground truth table multiplied with this year's score is always negative, right? Okay, this is basically when you implement your perception to test on real data set, how you should do. Any question? Everyone is good? Okay, let me emphasize, in your homework, please follow this. I have real steps to implement your perception. Okay? So now we're going to talk about our first variant of perception, which is called margin perception. Right? So now it connects to the margin, the concept margin. So why should we consider margin? Let us look at this artificial data set. Those are positive examples or negative examples. Obviously, this data is linear separable. There are many, like even infinite many separating hyperplanes. So I just draw 2 examples, each one is 2. Right? So now I want to ask you, which one do you believe can generalize better? meaning that in predicting future on same examples gives better prediction accuracy. Each one? Why?
Because it doesn't get close to any of the examples.
Yeah, of course. Yeah. So then why it doesn't get close to any type of examples can lead to better generalization performance. Any thought? Or any guess? Everyone believes this is the truth, right?
Is it because when you increase the margin, the number of errors you get increases?
I mean, from probabilistic sense, yes, you're right. There is some like proof in the computational learning theory about this. But here we just want to give some intuition and analysis, qualitative analysis. We'll get to this, more algebraically way later. Right? Okay, so your intuition is perfect and it's correct, right? So now let me give you some analysis why this intuition is rational, is reasonable, right? So we can observe that each one has a larger margin, much larger margin than H2, right? So the margin indicates how far away your boundary or hyperplane is from positive and negative examples, right? So obviously H1 is much further away from both positive and negative examples than H2, right? But what's the benefit? What's the advantage? Or in other words, if H2 is getting too close to those training examples, what kind of risk can it take? So the risk is as follows. So remember, the training examples are sampled from some underlying data distributions, right? So everyone knows the maximum likelihood estimation. The basic assumption is that okay, if this data are sampled, meaning that they are more likely to be generated, right? So basically, it implies that okay, the regions for dense positive examples and dense negative examples are high density regions of the data distribution, right? So that means, okay, if I generate new test examples, it's likely the positive examples will appear in these regions, right? Negative examples will appear in these regions, right? Now comes the risk, right? If your hyperplane is too close to those high density regions, like in H2, we can see that it actually passes through the high density regions for both positive examples, negative examples, and positive examples. What will happen? We can see that okay, H2 passes through the positive example, right? But it's likely that a new positive example to appear on both sides of this boundary, right? So it appears on this side is fine. It can correct predict it. But it appears on the other side. Or to make wrong prediction, right? And unfortunately, it passes through these high density regions. So it's very likely that you have another new test example which is positive but appears on the other side. And H2 can make a wrong prediction, right? And similar arguments, you can see that H2 passes through the high density region for negative examples. Right? So that means on the other side, you also have a high chance to meet a negative example, which H2 predicted as positive. So you can see that, okay, this is the risk, right? So the closer, the smaller the margin, the closer you are, the closer the hyperplane to this high density regions, meaning that the more likely on the other side of the boundary you come out example which you're going to predict as wrong. So now if you take a look at H1, we can see the benefit, right? Because each one is very far away from both positive and negative examples, meaning that it's far away from the high density regions for both positive and negative examples. Right? So now you can imagine, okay, I'm going to use each one to make prediction. All the positive examples on this side will be predicted as positive. Right? It's very rare that some positive example appear here. Right? Why? Because this is not high density region for positive examples. This is a low density region. It's unlikely that you're gonna misclassify positive examples on here. Right? And similarly, each one is also far away from high density region for negative examples. So when it makes wrong prediction for a negative example, that means some negative example appear here, right? But this is very rare. It's unlikely some negative example appear here because this is a low density region. So now we can see the benefit of large margin. In summary, the larger the margin, the farther away from both positive and negative examples, the farther away your hyperplane is from the high density regions. Right? And then the less risk you will take to misclassify those examples. Any question? Okay. And later we'll give some algebraic bound about generalization error. This will be even more clear. You see that, okay, the smaller, the larger the bound, the larger the margin, the smaller the generalization error bound. So that's why SVM is motivated to minimize the generalization error bound. Okay. So now we want to encourage our learned hyperplane by perception to have a large margin. How can we do that? We can fulfill that with the so-called margin perception. So in ordinary perception, we make updates when the prediction is incorrect, right? The prediction, if the prediction is incorrect, this can be characterized by this inequality, namely the product between the ground truth label and the decision score is negative, right? Is not negative or less than or equal to 0, right? So now we're going to change this triggering condition for the update. Replace this condition by this. So when this left-hand side is less than eta, and eta is positive number, then we're going to update. We're going to enforce our bit vector to be updated following the rule. So what does this mean? This is simply the distance, right? The distance formula, right? Of course, if you make a wrong prediction, we know that this numerator is negative, right? Of course, it will be negative number will be less than positive number, and you will have the weight. You will incur the weight to be updated, which is the same as the ordinary perception, right? However, even if you make a correct prediction, so this left-hand side is positive, but and which represents distance. But if this distance is less than this threshold, we're going to still enforce our weight vector to be updated. Okay? So just use this condition to decide if we're going to update or not. Okay? And keep doing this until converge or the maximum number of epochs is finished. Right? And in the end, if we suppose we have got a separating hyperplane, what's the property of this hyperplane? And so?
So put a bound, lower bound on your margin.
Yes, exactly right. So if finally running this perception, according to this condition, you end up with a separating hyperplane. What happens that this inequality will never hold, right? For every chain example, that means the left-hand side is always no less than eta, right? Remember, the left-hand side is distance. Distance, that means the distance between every chain example and the hyperplane is at least eta, right? So this says, okay, you find a separating hyperplane whose margin is eta, right? Or at least eta. That's why this is called a margin perception. Right? By setting up a eta, you run it, you guarantee to find a separating hyperplane whose margin is at least eta. Of course, you can choose a larger eta, you can try to choose a larger eta, right? So that, because from our analysis, we know that the larger the margin, the better generalization performance. You can try to enforce your perception to find a hyperplane with as large margin as possible. You can intentionally set a large margin. But of course, just be aware there are some consequences, right? Suppose you set eta to be too large, even larger than the margin of the data set itself. Will the algorithm converge? No, right? Because there doesn't exist any hyperplane for this data set that has that large margin, right? So it won't be able to converge. So a more practical suggestion will be, okay, you can gradually increase your eta. So starting from 0, you will end up with the ordinary perception result, right? And increase the eta a little bit and see if you can satisfy. If it's satisfied, you can keep increasing until some setting of eta doesn't work. It doesn't converge. Another suggestion will be, okay, I'm going to set up big eta at the beginning. Right? If it feels I just divide eta by half, then something like binary search. Okay, any question regarding the idea of margin perception? Okay. So the third variance, I think I'll just briefly cover the idea. So are motivated by the fact that many practical data are not linear separable. So in that case, in theory, perception won't guarantee to converge, and you have to set up the maximum number of updates or max number of epochs, right? So ideally, we want to find a separating hyperplane which can make a minimum number of mistakes. However, this is a kind of empty heart. You can now enumerate all possible hyperplanes and pick up which one has the smallest mistakes during training. Right? So this is infeasible, right? Only theoretically meaningful. And how can we alleviate this issue, right? So the first version is called the voted perception. The idea is, okay, I'm going to run my perception, right, until the maximum number of epochs are done. Right? Throughout this whole running procedure, we explicitly record all the distinct weight vectors showing up in the whole running procedure. Right? And for each distinct weight vector, we're going to record the life cycle of that weight vector. So life cycle includes how, if it correctly predicts one example, you just stay on there, right? And move to the next example. If it can also, if you still correctly predict that example, you stay there, right? Until some time it mistakenly predicts one example, its life is ended, right? And it is updated to a new weight vector. So we just count how many such examples it can pass through, can correctly predict, and we use this count to describe the importance of each distinct weight vector during the training procedure. So which are denoted by C1, C2 to CP. And finally, when we make prediction, right? When we make prediction, we use each distinct weight vector to make prediction. But their prediction is voted by the corresponding count, C1, C2 to CP. And finally, just look at which prediction has more total votes. Use that vote as your final. Use that winner as your final prediction. So this is very similar to how we combine weight classifiers in E-levels, right? And each distinct weight vector, and their counts is a particular classifier. Right? They just combine them. How to combine them? You just make prediction and use their volts. That is called a voltage perception. So we're gonna look into the details like how we create, how we track the life cycle of each distinct weight in the next lecture, and we'll see that voltage perception actually is quite expensive because you have to explicitly store the list of these weight vectors and their counts. So we will have actually much more economic implementations called average perception. We're going to discuss about them on Thursday. Next.